Hi everyone, so in this video we are going to learn about chapter 5, which is on work, energy and power. This is an overview for this chapter, so we are going to learn about energy first, and under energy we are going to learn about kinetic energy, principle of conservation of energy, gravitational potential energy and elastic potential energy, and under power we are going to learn about average and instantaneous power. Okay, first of all, work. How do we define work done? Imagine we have an object placed on a surface and then there is a force F acting on that object. Due to the force pushing on the object will move for a certain displacement S until it reaches its final position. So because there is F and also S, we can say that there is work done. So the definition is, work done by a constant force is a product of the component of the force parallel to the displacement times the displacement of a body, or we can also define it as the scalar or dot product between force and displacement of a body. We have learned about scalar product in chapter 1, in which we can write work is equal to F dot S, and if we expand this, we can get work in the form of Fs cos theta, where F is the magnitude of force, S is the displacement of the body, and theta is the angle between F and S. So work done is a scalar quantity and its SI unit is kg meter square per second square or joule. And what is 1 joule? 1 joule is the work done by a force of 1 Newton, which results in a displacement of 1 meter in the direction of the force. So let's say we have an object on a surface and then we apply a 1 Newton force on that object. What happens is that the object will be displaced by 1 meter, and if we calculate the work done, we will get work done is equal to 1 joule. And you also need to know the unit conversion. So 1 joule is equal to 1 Newton meter, and it's also equal to 1 kg meter square per second square. And then we have the force displacement graph, in which force will be the y-axis and then the displacement is x-axis. And since the force is constant, so we have a straight line for the force. And if we find the shaded area under the force displacement graph, we can find the work done. Okay, now we are going to look at applications of work's equation. So we have our first case here, in which work is done by a horizontal force F, which will cause the object to be displaced by S. And then we want to find the work done, so we use W is equal to Fs cos theta, and then we have to find theta, which is the angle between F and S. So our force is in this direction, and then we also have displacement, which is parallel to the force. So the angle between them is 0, and you can substitute in theta is equal to 0 here, which will give you Fs. For the second case, we have work done by a vertical force. So our force right now is in the vertical component, and the object will have a displacement S. And to find the work, we have to use work's equation. W is equal to Fs cos theta. Once again, find the theta by looking at the angle between force and also displacement. So here we have angle is 90 degree, and we can substitute in theta is equal to 90 degree in this equation, which will give us work is equal to 0 joule. For the third case, we have work done by two horizontal forces, F1 and F2, and we have displacement S. And in this case, we have two forces. So to find the work done, we have to find W1 and W2 first, in which W1 is the work done by force 1, and W2 is the work done by force 2. And then the total work done will be the sum of W1 and W2. And we can substitute in the equation. So we get F1S plus F2S, because the cos 0 is equal to 1. So we don't have to write that anymore. And we can factorize S. So we get F1 plus F2S. And F1 plus F2 is actually the net force, F net. So we can rewrite our equation as W is equal to F net S. So for the fourth case, we also have two forces. In this case, we have force F and also frictional force. And the difference here is that you can see force F has an angle to the horizontal. So for this, if we want to find the work done, we can do the same thing as we did for the third case, where we have two forces or more, and we can use W is equal to F net S. And this is actually equal to the net work. So using that formula, net work is equal to F net S, and then what we have to do is find F net. So this is where we have to apply the things we have learned in chapter 4. So in this case, we have two forces. And then basically what we have to do is draw the free body diagram of the object. So we have a frictional force to the left and force F with an angle to the horizontal. And now we would like to find what is F net. Since F has an angle to the horizontal, we can resolve it into Fx and Fy. So now we want to find F net, but how? Okay, so first of all, you have to look at the displacement. As we can see, the displacement is in the horizontal component or the x component. So what is causing the object to move is basically the net force in x component. So to find F net, we just have to look at the forces in the x component. So first of all, find Fx first. In this case, we have Fx is equal to F cos theta. And since our Fx is to the right, so we treat it as positive. So Fx minus friction, and then it will become F cos theta minus F. So now that we have our F net, we can substitute it into the W net formula. So we get W net is equal to F cos theta minus F times S. An alternative method would be to use F net is equal to MA, and then you replace F net is equal to MA into the W net equation. So we will get W net is equal to MAS. Okay, the question now is, when is work done 0? Let's look at the first example. We have a spacecraft which is traveling with constant velocity. So we know previously that if we have something that is traveling with constant velocity, then the acceleration will be equal to 0. And then if acceleration is 0, remember that F is equal to ma. So in this case, our acceleration is 0. So the force will also be equal to 0. And then we have to find the work done. So work done is equal to Fs cos theta. And our force is 0. So substitute in 0 here. And finally, we will get work is equal to 0 joule. Okay, for the next example, we have a person which is pushing on a wall. So there is force exerted on the building. And as you can see, because it is a wall, the wall will not be moving. So there will be no displacement, which means that S is equal to 0. So then we want to find work done and use the same formula. But now we substitute S is equal to 0. So finally, we will get W is equal to 0 joule as well. And for the third example, we have a car which is moving in a circular motion, and then there will be a centripetal force acting on the car towards the center of the circular path, and then the displacement will be along the velocity vector. So the angle between them is 90 degree, and then we replace the theta is equal to 90 into the equation of work, and then we will get work is equal to 0 joule. So work will be 0 when the force is 0, the displacement is equal to 0, and finally if the angle is 90 degree. Okay, now we will look at the sign for work. So we know that W is equal to Fs cos theta. If the angle between F and S is between 0 and 90 degree, if we find cos theta, what we will find is that the value of cos theta will be more than 0. And this will give us a positive value. So if cos theta is positive and we substitute that into the formula of work, then we will get work is more than 0 as well, which is also a positive value. Positive work indicates that the work is done on the system by an external force and energy is transferred to the system. Meanwhile, if the angle is between 90 and 180 degree, if we find the cos theta, we will get a value which is less than 0. and this is a negative value. So if we substitute in a negative value of cos theta, our work done will also be less than 0, which is negative. And negative work indicates that work is done by the system where energy is transferred from the system. Okay, now let's try and solve this question. We have a physics reference book which is push 1.5 meter along a horizontal table with a horizontal force of 5 Newton. So in this question, we are given the displacement and also force. And we are also given the frictional force, which is 1.6 Newton. Okay, we are asked to calculate the work done by the 5 Newton force, and we can write this as WF. And then the work done by the frictional force as W lowercase f. And the total work done on the book is net work. Draw a diagram first so that you have a clearer idea of what's going on. So we have a book on a table, and then there's 5 Newton force and also frictional force acting on that object. And then there will be a displacement of 1.5 meter. So to find the work done, we can use the formula of work, which is Fs cos theta. And then theta is the angle between force 5 Newton and also the displacement. The 5 Newton force is to the right and displacement is also in the same direction. So the angle between them is 0 degree. And then substitute in all the values into the equation. And you will get the final answer, 7.50 joule. Okay, for the next part, we want to find the work done by frictional force. We are still using the same formula, but in this case, our force is the frictional force. And then the theta is the angle between frictional force and displacement. The frictional force is to the left and then the displacement is to the right. So the angle between them is 180 degree. And then we substitute in all our values into the equation. So 1.6 times 1.5 cos 180 degree. And we will get work done is equal to negative 2.40 joule. For C, we want to find the total work done. So actually, you can just add the work done that you have calculated in A with B. But I will show you another method in which we will use the W net is equal to F net S. So to use this, we have to find F net. So F net, you have to look at the forces in the X component because the displacement is also in the X component. So from here, we can see that if we find the total net force for the X component, we will get 5 Newton force F minus the frictional force. And then we can substitute our net force into the work equation times by the displacement and then substitute in our values. So 5 minus 1.60 times by 1.50, which will give us 5.10 joule. Okay, moving on to 5.2, which is about energy and conservation of energy. So first of all, energy is a system's ability to do work. And then the SI unit for energy is joule. And energy is a scalar quantity. There are two types of energy that we will focus on. The first one is kinetic energy, K. And kinetic energy is an energy of a body due to its motion. And we can write the formula as K is equal to half mv squared, where K is the kinetic energy of a body, m is the mass of a body, and v is the speed of a body. And then we have the work kinetic energy theorem, which states that work done by the net force on a body is equal to the change in the body's kinetic energy. And this can be written as W net is equal to delta K, which is the change in kinetic energy, Kf minus Ki. Okay, now let's solve example 5.4. We have a stationary object of mass 3 kg and it is pulled to the north by a constant force of magnitude 50 Newton on a smooth surface. So here we are given the mass and then we are given the force, which is 50 Newton. And we are told it is on a smooth surface, so there is no friction. And then we want to find the speed of the object when it has traveled 4 meters away. So we have the displacement as well. Another information that we can get from the question is that the object is a stationary object, hence the initial speed is 0. So you can draw a diagram to visualize the question. So this is top view, meaning we are viewing this from above. We have an object which is pulled by a force with magnitude of 50 Newton. And then once the force is pulling the object will move for 4 meter. Since there is no frictional force, so there's only one force acting on this object, which is force F, and that will be equal to our net force. And then we want to find V, speed, so we have to use work kinetic energy theorem, because from the formula of kinetic energy we can get the speed. So applying work kinetic energy theorem, in which W net is equal to delta K, and delta K is Kf minus Ki. And then we have to find the net work, so we can use the formula that we have learned previously, which is W net is equal to F net S. And then Kf is equal to half mv squared, and Ki is equal to half mu squared. Now remember that the object is initially stationary, so it has u is equal to 0, hence our Ki will be equal to 0. So we are left with F net S is equal to half mv squared. And then what we have to do is just substitute in all the values that we have in order to find V. And solving this will give us V is equal to 11.6 meter per second.